Have you ever seen a cup of steaming hot water freeze faster than cold water? Have you ever watched a tiny droplet of water hover, glide, and dance across a blazing hot pan like it's alive? Or wondered why massive hurricanes spin counterclockwise in the United States, but flip direction? If you hop across the equator, or heard of a liquid so strange that it climbs walls, escapes its container, and flows with absolutely zero resistance? And what about waves, entire waves, that look frozen in place, even though they're vibrating at full speed? These aren't tricks. They aren't illusions. They aren't glitches in a simulation. They are real, scientifically verified physics phenomena that challenge how we think reality should behave. Today, we're going deeper than ever into 5 of the strangest phenomena that make scientists stare, scratch their heads, and rethink the rules of nature. Get ready. Your brain is about to enter the weird zone. 1. The Mpemba Effect. When hot water freezes faster than cold water, this is one of those effects that makes everyone go, "No way, that's impossible." But under the right conditions, hot water truly can freeze faster than cold water. This is the Mpemba Effect, named after Erasto Mpemba, a Tanzanian student who rediscovered what Aristotle described centuries earlier. So why does this happen? Let's unpack the possible explanations. Theory 1. Evaporation. Hot water evaporates faster, gives less water, gives quicker freezing. This alone doesn't fully explain the effect, but it contributes. Theory 2. Convection current. Hot water circulates more aggressively. This increased motion redistributes heat more efficiently, allowing the temperature to drop faster. Theory 3. Hydrogen bond rearrangementhiating water disrupts its hydrogen bonding network. As it cools, the molecules may align more efficiently into ice crystals. Theory 4. Freezer and environmental effect. Hot water can melt nearby frost, giving it better thermal contact. Cold water doesn't, so it may sit in insulating ice crystals. Real-world exemplifying extremely cold winters in Canada. People sometimes observe boiling water thrown into the air turning into snow instantly. While that's not exactly the Mpemba Effect, it demonstrates how temperature, evaporation, and environment interact in surprising ways. The Mpemba Effect doesn't happen every time, but when it does, it reminds us that common sense is often just incomplete science. 2. The Leidenfrost Effect. Water that floats on vapor. If you've ever cooked on a sizzling skillet, you've seen this. A droplet of water hits the pan. Then instead of evaporating, it dances around like it's doing ballet. This is the Leidenfrost Effect. When a surface is far hotter than the boiling point of water, the bottom layer of the droplet vaporizes instantly. That vapor creates a protective, insulating cushion that keeps the droplet lifted off the pan. The droplet literally rides on its own steam. Why it happens? Heat transfer slows down because the droplet isn't touching the surface. This makes it last longer, not shorter, which blows people's minds. Fun fact: if you wet your finger and very quickly tap a burning hot surface, Leidenfrost protection can keep you from being burned. Though don't try this unless you know exactly what you're doing. Where else it appears? Lava-water interactions, industrial cooling, drops on extremely hot metal rails, even liquid nitrogen droplets on warm floors. This effect shows that sometimes the hotter something is, the safer it becomes. A total reversal of intuition. 3. The Coriolis Effect. The planet's giant invisible hand. Now, let's scale up, way up, to the size of an entire planet. The Coriolis Effect is the reason hurricanes spin counterclockwise in the US and clockwise in Australia. It's why trade winds curve. It's why jet streams twist across North America like giant atmospheric rivers. The simple explanation: Earth is rotating. Different latitudes move at different speeds. Air moving long distances gets shifted sideways relative to the ground. In the northern hemisphere, everything bends to the right. In the southern hemisphere, everything bends to the left. What this means: storms don't just spin for no reason. They spin because Earth is literally twisting beneath them. Myth-busted toilets, sinks, and bathtubs don't drain differently due to the Coriolis effect. Those systems are too small. Plumbing design completely overrides Earth's rotation. But on the scale of thousands of miles, Coriolis is the dominant force shaping weather patterns. Without it, the climate of the US and Canada would look completely different. Storms wouldn't rotate the same way, jet stream paths would shift, and entire seasonal patterns would collapse. It's the atmosphere's built-in steering wheel. For superfluidity, the liquid that defies reality, we step into truly alien physics, the kind that feels like science fiction. When helium is cooled to just above absolute zero, it transforms into a superfluid, a state of matter with zero viscosity. What does that mean? It means the liquid can flow endlessly without slowing, creep up the sides of containers, leak through microscopic holes, move as if it has no internal friction at all, spread out across a surface like a living film imaging spinning a glass of normal water. It slows down quickly, but spin a container of superfluid helium, and it will keep spinning virtually forever. Quantum mechanics at work at extremely low temperatures. Helium atoms fall into the same quantum state. They act not as individuals, but as one cohesive wave. This collective behavior eliminates internal resistance. Superfluidity reveals a universe that behaves completely differently at ultra-small scales and ultra-low temperatures, a universe defined by wave patterns, not particles. Scientists study superfluids to understand quantum vortices, superconductivity, neutron stars. Early universe physics. Superfluid helium is basically the universe showing off. 5. Standing waves motion that looks frozen finally. We bring it home with one of the most beautiful and mysterious effects, standing waves. A standing wave forms when two waves moving opposite directions overlap perfectly. Instead of traveling, the wave appears to oscillate in place. Certain points, called nodes, don't move at all. Other points, antinids, vibrate with maximum intensity. Where you've seen this. The strings of a guitar or violin. Waves in a glass of water when someone taps it. The infamous Tacoma-Narrows Bridge collapse. Sound waves in your vocal tract. Microwaves heating food unevenly. Vibrating air columns in flutes and pipe organs. Ripple patterns on speaker surface. Standing waves create stable patterns, almost like nature's geometric signature. They're the backbone of music, engineering, and even quantum mechanics. Inside atoms, electrons behave as standing waves around the nucleus, not as little planets orbiting a sun. In that sense, standing waves describe how matter is structured on the most fundamental level. Asterisk physics is supposed to be logical, predictable, strict. But the deeper we go, the more we find phenomena that challenge everything we assume about the universe. Hot water freezing faster than cold. Droplets that hover on vapor. Storms controlled by the planet's rotation. Liquids that climb walls and flow forever. Waves that stand still, frozen in time. These aren't exceptions. They're reminders that reality is far stranger than our instincts. If you love exploring the bizarre, beautiful, mind-bending side of science, hit follow, drop a comment, and tell me which phenomenon you want to see next. Stay curious, stay fascinated, because in physics, the weird parts are usually where the truth hides. See you in the next one.